Good morning, student. Today's topic of this video lecture is electric dipole and electric dipole moment. Though it is a topic of chapter number 1, that is electric charge and electric field, but since in chapter 2 we have to derive electrostatic potential energy and electrostatic potential of electric dipole, so it will be beneficial for us to revise this electric dipole and electric dipole moment before starting the electrostatic potential of electric dipole and potential energy of electric dipole. So let's start and let's revise what is actually electric dipole and electric dipole moment. So what is electric dipole? Electric dipole is basically, how can we define electric dipole? Is basically a system of two equal and opposite charges which are separated by a very small distance d. So this system, the system of two equal and opposite charges which are separated from distance d or displacement d, is called electric dipole. This is called electric dipole. So electric dipole, again I define, it is a system of two equal and opposite charges which are separated by distance d. And now what is electric dipole moment? Electric dipole moment is represented by P, and as you can see here the arrow sign, that means it is a vector quantity and it is the product of any of the charge, because both the charges are equal, the amplitude are same, so any of the charge and the distance between these two. So the product of charge and displacement is called electric dipole, and it is a vector quantity. It is a vector quantity, so remember this thing. Electric dipole is the different thing and electric dipole moment is the different thing. Electric dipole is basically, it is a system of two equal and opposite charge separated by distance d, and electric dipole moment is the product of q, that is charge, and the distance between these two. So it is a vector quantity. Electric dipole moment is a vector quantity. This is electric dipole moment, and this system is called electric dipole. So this you should keep in your mind, what is electric dipole and what is electric dipole moment. And since it is a vector quantity, P is a vector quantity, so if P is a vector quantity, then it must have a direction. So what direction we consider for it? And it is taken as minus q2 plus q. Always the direction of electric dipole moment is taken as from minus q2 plus q. Say for example, this is the direction. In this case, this is the direction, that is positive x-axis. Say for example, I have two equal and opposite charges, minus 1 coulomb and plus 1 coulomb, right? Minus 1 coulomb and plus 1 coulomb, and it is separated by 5 meter, right? So electric dipole moment in this case is written as charge multiplied by distance, that is 5. And what about the direction? So it is from minus 1 coulomb to plus 1 coulomb, so it is toward the positive x-axis, that is we can write 5I. So this is the electric dipole moment is written as 5I in this particular case. In the same way, if electric dipole moment is like this, minus 1 coulomb and plus 1 coulomb, and here the distance between is 5 meter, so what is the electric dipole moment? It is minus 5I, because it is in the negative x direction, and negative x direction is represented by minus I. In the same way, if it is in like this, minus q to plus q, then the direction is represented by j, right? So you can easily find out what is the value of. Now suppose if the electric dipole moment is represented like this is minus 1 coulomb and this is plus 1 coulomb and this is 5 meter and it is making angle 30 degree from x-axis, then what is the P, what is the electric dipole moment? This you have to find out, and you can easily find out what is the value of electric dipole moment. If you have any problem, then you can ask me. So I leave it this question for you to solve, right? Now the next is unit of electric dipole is electric dipole moment is, as you can see here, it is q, the charge. The unit of charge is coulomb, the unit of distance is meter. So coulomb meter is the unit of electric dipole. Now what about the dimension? Dimension is dimensional formula. Coulomb is basically charge q is equal to, we know that, current into time, and I is the current, it is the time, and current is the fundamental unit and it is represented as A and time as T. So here in place of coulomb we can write AT. In place of this, length is the L is the dimensional formula for length, for distance, for displacement, so it become LTA, or in a expansion form we can write m to the power 0 LTA, because there is no mass. So the dimension formula is this one. So this is all about electric dipole and electric dipole moment. Now see what is the torque. And why we are using torque in case of electric dipole? It is because a torque is basically a turning effect of force, and as you can see here, this is the black line is represented electric field line, and it is toward the positive x direction. It is uniform electric field. As you can see, all the lines are parallel to each other. So, and if we place electric dipole, as you can see from the red line, this is minus q, this is plus q. So the direction of this electric dipole is, if we place this dipole in this electric field making angle theta with the electric field, then what happens? In this case, a force start acting on the upper charge, that is plus q, in this direction. It is given by F is equal to QE, and in the negative side, negative q, it also experiences a force in the opposite direction, and it is given by F is equal to minus QE. Due to this, remember this thing, both the force are equal and opposite. Due to this, this force tend to rotate it in this direction, the electric dipole, and it is in this direction. So what happened? The electric dipole start rotating like this, clockwise direction, right? And it is because two equal and opposite forces are acting. So they are equal and opposite force. So F net, remember this thing, F net on the electric dipole is 0, but tau, that is torque, is not equal to 0. There is some torque, that is why it is turning, it start turning the electric dipole, but the net force on this dipole is 0. So how can we find out the torque? In the class 11th we have already defined the torque, and how can we find out the torque? And according to the definition of the torque is equal to force into perpendicular distance. Either of the force, there are two forces which are acting, it is a pair of force. So either of the force multiplied by the perpendicular distance between the line of action of the force. So this is the line of action of this force, this is the line of action of this force. So perpendicular distance is this one, that is given by AB. So we can write perpendicular distance as AB, and AB, as you can see here, if the length of this dipole, the displacement between the two charges is L, and if it is making angle theta, if this is theta, then this is also theta. So what is the value of AB? AB is equal to L sine theta. We can write L sine theta. So if we put over here AB is equal to L sine theta, so torque become F into L sine theta, and F we all know that Q into E. So if we write T, tau is equal to Q E L sine theta. So tau is equal to Q, E is the electric field, Q is the charge, L is the distance between the between the charges of electric dipole, and sine theta, it is theta is the angle between electric field and electric dipole, right? In this direction, in anti-clockwise direction we have taken. So this is equal to TE is equal to QEL sine theta, and if we arrange it in a proper way, then it is like tau is equal to Q L E sine theta, we can write. And why we have written like this? Because Q into L is equal to electric dipole moment and PE sine theta. So there is a relationship between electric dipole and electric field. So what is the relationship? Tau is equal to PE sine theta, where theta is the angle between electric dipole and electric field. So tau is equal to PE sine theta, and if you know what is the cross product, then we already know that cross product of any two vector quantity is given by AB sine theta A cross B is equal to AB sine theta. So here also we can T is equal to P sine theta. So if this is given, we can convert into this form. Here we can write this expression as tau is equal to P cross E. So this is the vector form of torque, and obviously torque is a vector quantity. It is also vector quantity, and whose direction is represented by the right hand screw rule. You can represent it. So this is all about the torque, and this is all about the electric dipole and electric dipole moment. So this is, again I revise, this is electric dipole, system of charges, two equal and opposite charges separated by a very small distance. Electric dipole moment is basically it is a product of charge into displacement, and then torque, which is very important. And torque is the basically turning effect of force, and whenever we placed electric dipole in a uniform electric field, then it experienced two equal and opposite force in this direction, which start rotating it in the anti-clockwise direction, and it is due to the torque which is produced by two equal and opposite force. And remember this thing, that the total net force in this dipole is 0, but torque is not equal to 0, and we have already derived the expression for torque. Tau is equal to P sine theta and P cross. Just remember these two terms, because when we derive electrostatic potential or electrostatic potential energy of electric dipole, then these two expressions will definitely come into use. So thank you for patient hearing.